Welcome to the Digital Electronics course. What is digital electronics? Digital electronics can be defined as the branch of electronics that studies digital, binary, or logical devices, circuits, and systems. Unlike linear or analog electronics, which work with signals that can take on a wide range of voltage values, voltages in digital electronics are restricted to taking on one of two values called high and low logic levels or states 1 and 0. Generally, a high or 1 logic level corresponds to the presence of voltage, and a low or 0 logic level corresponds to the absence of it. To better understand the concept of a digital system, let's take a simple electrical circuit as an example formed by a battery, a lamp, and a switch, figure 3. In this scenario, a high level or 1 logically represents the situation when the switch is closed and the lamp is turned on. Figure 3a. The low level or 0 occurs when the switch is open and the lamp is off. Figure 3b. In reality, digital circuits are simply a combination of numerous very fast switches that open or close at a given moment, forming specific patterns of 1s and 0s used for various purposes within electronic devices. In practical digital circuits, the logical states 1 and 0 correspond to two clearly defined voltage levels or ranges. The output of a digital circuit assumes only one of these two values in response to one or more inputs that can be either high or low. The topic of voltage logical levels, as interpreted in digital circuits, is detailed in Lesson 1. In digital terminology, the logical levels or states 1 and 0 are referred to as bits. The term bit is a contraction of binary digit. All electronic digital systems handle information in the form of bits, that is, 1s and 0s. A bit 1 or 0 can represent the on or off condition of a lamp, the closed or open state of a switch, the presence or absence of a hole in a punched card, a mark or a space in telegraphic communication, the value of 1 or 0 in a binary number, etc. Analog circuits and digital circuits. Electronic circuits are generally divided into two main categories: analog circuits and digital circuits. This division is based on how they control the signals that flow through them. Analog circuits work with a wide variety of signals that vary continuously within certain values, figure 5a. Analog circuits are also referred to as linear circuits. The digital or logic circuits operate with signals that can only take one of two possible values, figure 5b. At any given moment, the inputs and outputs of a digital circuit are either high or low, but not at an intermediate value. Using the circuit from figure 3 again as an example to clarify these ideas, we can assert that it is a digital system because the switch can only be open or closed, and the lamp can only be on or off. If instead we replace the switch with a dimmer switch as shown in figure 6, this circuit ceases to be digital and becomes a linear or analog circuit. If, instead, we replace the switch with a dimmer switch as shown in figure 6, this circuit ceases to be digital and transforms into a linear or analog circuit. This is because by turning the knob slowly, we can achieve a continuous variation in the lighting, ranging from a minimum value to a maximum value. Examples of analog electronic devices include radios, televisions, sound equipment, and communication devices. Due to their characteristic of adopting only one of two possible values, digital circuits are successfully used in applications where precision and reliability are required. Among the main digital devices are clocks, calculators, computers, and measuring instruments. These systems deliver exact processes and/or receive signals, as a digital signal is either on or off and does not allow for intermediate positions. In general, digital circuits are characterized by handling information in the form of bits. As we know, a bit or binary digit represents the state or condition, 1 or 0, high or low, of a digital signal. The bit is the basic unit of information for any digital system. From the simplest computer to the most sophisticated microcomputer, a digital circuit can have one or more inputs and one or more outputs, Figure 7. The logical level or state of each output depends on the state of each input and the specific function for which the circuit has been designed. Both analog and digital circuits can be implemented in practice using discrete components or in integrated form. Discrete component circuits consist of transistors, resistors, diodes, capacitors, and other individual devices interconnected on a printed circuit board, see Figure 8. In an integrated circuit, all components are manufactured together on a silicon wafer or chip. Regardless of their construction, discrete or integrated, the fundamental difference between an analog circuit and a digital one lies in how each one uses or processes electric current. Analog circuits basically amplify the current, while digital circuits simply switch it between one value and another. This allows them to perform incredibly complex functions reliably, quickly, and cost-effectively. Many current systems are hybrids, meaning they simultaneously handle analog and digital signals and must process them in both analog and digital forms to obtain input and output information. The most well-known hybrid systems are those used for industrial process control, where analog quantities such as temperature, speed, time, etc., are measured and controlled. Once this analog information is obtained, it is converted into digital information to facilitate its processing through digital circuits such as counters, comparators, microprocessors, etc.